All right, last one. So a 0.2 kilogram object is attached to a spring with a spring constant K, which is 10 Newton meters, and moves with simple harmonic motion over a frictionless surface. So basically you have this setup, there's a spring, there's a box on that spring, and the thing goes back and forth like that. So there's an oscillating system. At the instant that is displaced from equilibrium by this far, what is its acceleration? Okay, so basically they want to know the acceleration. So whenever they ask for acceleration, think about F equals ma, force over mass. So all I need is the force and the mass, and I can get acceleration. They gave us the mass. Obviously, they didn't give us the force, but they did give us the spring constant. So force is equal to K times X. So K is 10. They gave us that in the problem. And the extension they mentioned was this, negative 0.05 meters. And so multiplying that, 0.5, well, it's supposed to be negative. We'll see if that has anything to do with it, but I doubt it does. Negative 0.5 newtons is going to be the force. And so negative 0.5 divided by the mass of 0.2 gives me the acceleration, 0.5 divided by 0.2 gives us 2.5 meters per second squared, like that. All right, and that is an option, and it is D. Okay, so even though it's an oscillating system, sometimes they don't really ask you about the oscillations. A mass on the spring vibrates in simple harmonic motion at a frequency of 4 hertz and an amplitude of 4 centimeters. If a timer is started with a displacement is a maximum, hence 4 centimeters at time 0, what is the speed of the mass when it is at time equals 3 seconds? This is a great question. So a mass on a string vibrates with simple harmonic motion. Okay? Mass on a spring. Oh, I'm sorry. Mass on a spring, not mass on a string. That would be weird. So it's basically the same setup as the problem before, going back and forth like this. Now, they give us a frequency that it oscillates at 4 hertz. And the amplitude is 4 centimeters, so 0.04 meters. Okay? And they say there's a maximum displacement, okay, of 4. Because, yeah, the maximum displacement is the amplitude. Then what is the speed of it when it is at this point? Now, this is an interesting question because it is talking about where is it at this point. It wants to know its position, and then it wants to know an energy calculation. So we'll do the energy calculation in a second, but first, let's talk about how we can learn where the heck this is. So that takes us to applying this equation, okay, for position of a oscillating system, okay? What is that? No, that's not important. Anyway, so this is an equation on your reference table. It tells you where an oscillating system is at any given point. Now the amplitude they gave us was 0.04 meters. That's good. Cosine of 2 pi, I know all those numbers. They gave us a frequency. The frequency was 4 hertz. And the time they gave us was 3 seconds. So plugging it all into this equation, we should be able to get its position. So 0.04 times cosine of 2 pi times 4 times 3. All right. And so that gives me, ooh, I made a mistake. You want to make sure whenever you're doing these calculations that your calculator's in radian mode. Very few times when you want your calculator in radian mode, but you want to do it when you're dealing with angular displacements, and you want to do it when you're dealing with oscillations, like this. So, switching to radian mode, 0.04 times cosine of 2 times pi times 4 times 3. Okay? That gives me 0.04 meters, like that. Really? That would be amazing. Hold on, one more check because I don't believe it. I don't think I did anything wrong, but we just got to make sure. So cosine of 2 times pi times 4 times 3 gives me, its location would be at 4 meters. Okay, very cool. So I'm guessing this makes sense because we only have whole numbers here. and 2 pi is a full rotation. That's my guess. So we're going to have a multiple of 2 pi in there, which means we're going to have a multiple of the full oscillation. Anyway, so if that's our location, 0.04 at that location, then what is the speed? Well, this makes it actually a lot easier. Because if you think about an oscillating system, so I'm going to draw 3 boxes. The middle box will be at the 0 line, the equilibrium position, okay? This one will be at the max amplitude, x is equal to 4 centimeters. This one will be equal at the smallest amplitude, or the minimum amplitude, which is negative 4 centimeters. Centimeters. Okay. So at this point is when the velocity is at its max value, because it's in the middle. At these 2 points, the spring is trying to pull the block back as it goes over here, and so the velocity will be 0 here. Velocity will be 0 here. Now, this problem is a balance of the potential energy of the spring, okay? So at its maximum value, that should be its total energy the whole time. And that should be equal to the kinetic energy it has of motion plus the potential energy that's still in the spring. Now, if this block was here, what we would have to do is we'd have to figure out what that location is, figure out how much potential energy is still in the spring, and then solve the equation to solve for the speed. But because the block is at its maximum position, speed is equal to 0. So let's look at the options. What is the speed at 3 seconds? 0, because it's at its maximum value where it's not even moving. Last question. Consider the curve x equals a sine of kt. Okay, so they gave us a different equation for the position of an oscillating system with a greater than 0. Good, that means it's moving. At which point on the graph is it possible that t is equal to 0? Okay, so of all these times, which one is it possible that t is equal to 0? Well, that would mean a sine, well, if t is 0, then that would mean sine would be 0. And I've shown you guys plenty of times in class, sine of 0 is equal to 0. That means the whole thing would be 0. So in order for one of these values to be time equals 0, the graph would have to equal 0. So it would have to cross the x-axis, which is possible at t1, possible at t3, not possible at any other location. At which point on the graph is it possible? Well, I guess it would just be t1, because that is at the 0 mark. No, it's got to be t3. It's got to be t3, not t1, because if time is equal to a positive number, let me explain this. Okay, if you have a graph and you graphed sine by itself at 0, it would be 0. But then if you plugged in the next number and you graphed a sine function, it would look like this. It would continue up after the 0 mark. The only part of this graph that continues up after 0 is t3. So I thought it was t1 because it came first, but I was wrong, because t3 is the only point that continues upward after being at 0 point. So that would mean point t3 is our final answer, is the answers for all of the problems.